In this lesson, we're going to be looking at springs and specifically the force that springs exert on objects that are attached to the end of these springs. Now, a couple of things that are important up front. One is that we are talking about ideal springs. So these are like physics textbooks springs, meaning we are going to assume the springs themselves are massless. We are going to assume that the stretch and compression of the springs does not generate any heat or energy loss, so that the springs are ideal, perfect springs. Now, the other thing that we're going to be considering with these springs is that these are springs that have space between the coils. So it's kind of like a shock absorber, or I'll even say like a tigger's tail type of a spring. They're bouncy, bouncy, bouncy. Fun. So what we have here is a situation where the spring initially, we are going to say, is at this position, 0, when it's unstretched. So we had to pull it to the right and stretch the spring to get it to this position. Now, when we pulled it to the right to get it to this position, the spring is pulling back, and that's what springs do. They pull and they push back. They basically want to be at position 0. So if we pull the spring to the right, the spring will want to pull back to position 0. If we compress the spring to the left, the spring again would want to push back and put it back to position 0. So what we have over here is simply the force diagram. If there's no friction between the block and the ground, the only force acting on it would be the spring force pulling back to the 0. We have gravity mg, and of course the force normal keeping the block from sinking into the ground. Now, we have here, as you can see, Hooke's law is what we call the force equation. Hooke's law is F equals minus kx. So that's an experimental result that Hooke determined was the behavior that was observed when you pulled on a spring. So in other words, the more force you pull on a spring with is corresponding directly to the amount of stretch that the spring is stretched. And the K in this equation is called the spring constant. And if we look at the units in this equation, the force is in newtons. X, of course, is in meters. So to make this equality work, that means K has to have units of newtons divided by meters. So the meters cancels out and we're left with newtons. And newtons per meter, that spring constant, you definitely want to think of as a strength parameter, meaning read it literally, newtons per meter. How many newtons it takes to stretch a spring 1 meter. So the bigger that number, the more newtons you need to stretch the spring 1 meter. The other thing about Hooke's law is we can see the force is linear with position, meaning the more you stretch the spring, the greater the spring force is pulling back to 0. So if we consider over here force as a function of x, we'll have a linear relationship. So force is the y-axis, x, of course, is the x-axis, and k is the spring constant, which is going to be our slope. So the steeper this linear line, this linear function is, the stronger the spring, and the shallower the slope, the weaker the spring. So the k equals the slope. The negative in this equation is thrown in. It's thrown in, it's contrived, right? So we're putting the negative into the equation, or Hooke put the negative into the equation to make sure that the spring force is always going to oppose the pull or the push. So when that x vector, which will be positive or negative, positive for a pull, negative for a push, that the spring force is going to react in the exact opposite sense and that's why the negative is there. Okay. Often to problem solve, I will not strictly use f equals minus kx. So often I find it very useful to problem solve by looking at the actual question, seeing whether the spring is pulling back to zero or pushing back to zero, and making sure that my spring force direction that I'm going to use in my force diagram is consistent with what I know the spring is doing. So regardless of the negative in the equation, I know the spring force here is negative because it's pulling to the left. Okay. The last part of the notes for this introductory lesson to springs is really, really, really important. So this part is super important. F equals ma never goes away. So if the spring force is the only force acting on an object, then we have F equals minus kx equals ma, and look at that equation. When we solve that equation for the acceleration, we get the acceleration equals minus k divided by m times x. That is not constant acceleration. That is acceleration that changes with x. So the bigger the x value, the greater the acceleration at any point in time. And the bottom line is literally the bottom line on this page of notes, is that you can never, ever, ever, cannot, not, ever use the constant acceleration equations when solving spring problems. That is why we're in the energy chapter, because we are going to be using energy to problem solve spring problems, and that is what we are going to introduce in the next lesson. For this lesson, I want you to certainly annotate everything that we've talked about here and be able to discuss this introduction to springs in class.